So now that we've introduced heat engines, I'd like to and we've introduced their efficiency, I'd like to see how efficient is the most efficient possible engine. You would naively think that would be 100%, but that turns out not to be the case. So let's think about what we could possibly have. The thing that we're going to require from our heat engine is that it be perfectly reversible. And why is that? Well, if it's perfectly reversible, it means that we can run the process forwards or backwards. And the only thing that would change would be the sign of all the thermodynamic variables. So, by the second law of thermodynamics, if I were to run this for a cycle, the entropy would either have to not change or increase. That would be true if I run it forward. It would also be true if I ran it backward. The only way that both of those can be true at once is if the change in entropy is 0. So there is a corollary to this, and that is that if you were to run it as such a perfectly reversible engine as backwards as a refrigerator, the effect of the devices would cancel. So say I have my hot reservoir, I have my cold reservoir. If I were to connect a perfectly reversible heat engine, so we extract some heat Q hot from the hot reservoir, Q cold from the cold reservoir, reject Q cold to the cold reservoir, and bring extracting useful work WS out from it, I can take that work and input it into another copy of this perfectly reversible heat engine that I'm running backwards as a refrigerator. And since the only thing that would change is the sign of the thermodynamic variables, the same amount of heat Q cold that got rejected into the cold reservoir here, that would be being extracted from the hot reservoir, extracted from the cold reservoir. And whatever I extracted from the hot reservoir here with the engine would be rejected to the hot reservoir with the refrigerator. So all of this would net out to be as if I didn't have any heat flows at all. So Q hot would be 0. My work that I would get out of this would be 0. And Q cold would be 0. So that is a corollary of our perfectly reversible heat engine. So if we were to, as I alluded in an earlier video, if we were to have something that was more efficient than a perfectly reversible heat engine, which we can't, but if we could, that would give us something where we could net out having a spontaneous flow of heat from the cold reservoir to the hot. However, we can't have such a engine that's more efficient than that's better than a perfectly reversible engine, because then we would be running into the problems of entropy changes not working in both directions. So we can't have, as a result, it is impossible to have a spontaneous flow of heat from cold to hot. So this violates the second law of thermodynamics, because otherwise what would happen is we would have a overall decrease in the entropy of the system, which isn't possible. Now, as a practical matter, we're not even going to be able to do as good as a perfectly reversible engine. Why is that? And that's because with a perfectly reversible engine, you can actually draw it on a PV diagram. It would follow the quasi-static process assumption. This would mean that it would take literally forever to run a cycle. So in the real world, anything that we do is not going to be perfectly reversible. And so it means it won't be as efficient as as if it were perfectly reversible. We would be rejecting excess heat to the cold reservoir, and we wouldn't be able to transfer it back out in this lane, so we wouldn't have a disconnection. We would have a net transfer of heat from hot to cold, for instance. Okay, so let's try to figure out, for such a perfectly reversible heat engine, in other words, one that I can actually draw the diagram for, what is the most efficient possible cycle that it could run? This turns out to be a thing called the Carnot cycle, spelled C-A-R-N-O-T. Now, to obtain it, I'm going to introduce a new diagram. We've seen PV diagrams before, so now we're going to have a TS diagram. So, same kind of idea. I'll put the temperature here and the entropy there. And say if I were to have an isothermal expansion, for instance. So this is my initial, that's my final, like that. The heat that would be transferred into the engine would be equal to the area under the curve. And this is because we saw that the change in entropy was integral initial to final of that funky d bar q over t thing that we saw before. We saw that for constant t, that worked out to delta S equals q over t, or q equals t delta S. So for constant temperature here, this would be equal to the heat either being transferred in or out. So if it's going left to right, that's heat going in. And if we're going from right to left, that's heat going out of the engine. So if it were something other than isothermal process, we can still argue that the heat extracted would be equal to the area under the curve. So say for some less efficient process, I'll draw it in purple. Let's say it looked something like that. Since this temperature here is the temperature of our hot reservoir, what we could imagine doing is, for whatever process we have, we could imagine approximating the process with a whole bunch of zigzags. Anything horizontal would be an isothermal process. Anything vertical would be an adiabatic process, so there's no heat transfer. So we could cut it up into a whole bunch of rectangles that are bounded by the isotherms, and for each of the different isotherms. And so then for a less efficient process, the heat transfer would be the area under this curve, for instance. And it doesn't have to be like that. We could instead say if it were, we had some less efficient process that connected down to a lower temperature like that, it'd still be the same issue. We would be missing this bit of area right here. Okay. So then what we want for our most efficient possible cycle is we want to extract maximal heat from the hot reservoir. And we want to reject minimum heat to the cold reservoir. And so this is the Carnot cycle. So in order to extract maximum heat while connected to the from the hot reservoir, it turns out we need an isothermal expansion. So this temperature here will be the temperature of the hot reservoir. And then because we don't want to lose any from the reasons I was mentioning before, we need to drop down to our colder temperature. I'll call this point A, this point B. We need to drop down to our colder temperature using an adiabatic expansion. So this is an isothermal expansion. remember for an adiabatic expansion, we saw that the change in entropy is 0. And then we can go ahead and return back. Now here we want to lose as little heat to the cold reservoir as possible. So to do that, we want to use an isothermal compression. Anything else, you would be operating at some higher temperature for a moment. So you'd be getting something like this, and we would be rejecting this excess heat to the cold reservoir, which we don't want to do. We want to reject as little as possible. And for the same kind of reason, to finally bring it all back home, we want to complete this using an adiabatic compression. Well, that was supposed to be vertical. There we go. Now, how do you actually achieve adiabatic expansions and compressions? In practice, you can't. This is an ideal. There is a process called the Stirling cycle that gets really close to this, but not quite. So anyway, between this, we will have extracted as much heat from the hot reservoir as possible. So we'll just extend down here. So everything I'm cross-hatching in red is heat we extract from the hot reservoir. Now this bit here, where we're going from right to left, this is where we are rejecting heat to the cold reservoir. I'll cross-hatch that in purple. So the heat we reject to the cold reservoir will be this smaller area under the curve. So the difference between those two, by the first law of thermodynamics, since we're running a cycle, delta E thermal is 0, means that the work we get out of this is going to be the difference between the Q hot and the Q cold. So this area here that I'm going to cross-hatch in green. There. So that's the useful work we get out of the system. And since we got running clockwise, that's positive work. This is a heat engine. If we were running it counterclockwise, that would be negative work, meaning that we were doing work was being done on the system. Then we would be running it backwards as a refrigerator. Okay, so this would be a good moment for you to pause the video, and I want you to go ahead and draw the corresponding PV diagram for this. And then after that, we'll go ahead and figure out what our efficiencies are. Okay, so our PV diagram is going to look something like this. So PV. So for our same points A, B, C, D, I'm going to identify this is the isotherm that corresponds to the temperature of the hot reservoir. This is the isotherm that corresponds to the temperature of the cold reservoir. So our first step will be an isothermal expansion. So this is our point A, that was our point B. And then to get down to the colder temperature, this is going to be an adiabat. So then we will go ahead and do our adiabatic compression. And then we'll go ahead, sorry, adiabatic expansion. And then we will go ahead and do our isothermal compression at the colder temperature, and finally return back with our adiabatic compression. Now, again, keep in mind, you can't build this for real because, for one thing, it would take literally forever to run, and for another thing, nobody has any idea how you would actually achieve these adiabats. Now you can get very close. The Stirling cycle replaces the adiabats with isocores, so constant volume processes, and that is one of the most efficient engines that you can make. Tends not to be used in things like cars or whatever because it runs slowly. Since it runs slowly, you get a lot of energy out of each power stroke, but the power strokes don't come around too frequently, and so it makes for a very bumpy ride. So Stirling engines tend, with the exception of ones used for demonstration purposes, Stirling engines tend to be very large. And they do actually have their uses. There's one example, for instance, of a facility that is taking a zillion mirrors to use energy from the light from the sun to heat up the gas. That's the working substance of the Stirling engine. And it runs just this really big Stirling engine and uses it to generate electricity. Anyway, the work is still going to be the area that we get out of this, is still going to be the area enclosed by the diagram. Now we only will have heat transfers along the isotherms, so we will have all of our heat coming in from the hot reservoir during this isotherm, and all of it being rejected to the cold reservoir during that isotherm. The adiabats have no heat transfer. Which is why it's as efficient as you can be. So what we've done is we've made this area here, the work, as big as we can by extracting as much heat from the hot reservoir as possible and rejecting as little to the cold reservoir as possible. Anything else will give us some shape that cuts out of this box and means that we will either be taking less heat from the hot reservoir than we could, or rejecting more heat to the cold reservoir than we need to, or both. Okay, so let's figure out what the efficiency of our Carnot cycle is. So if we go and look at these processes here, the change in entropy for an entire cycle, because it's reversible engine, has to be 0. But that's going to equal the change in entropy going from A to B, the change in entropy going from B to C, the change in entropy going from C to D, and then finally the change in entropy going from D back to A. Now, B to C and D to A are both adiabats. So B to C and D to A being both adiabats, we saw that for an adiabatic process, the entropy does not change. Now these are isothermal processes, so we will have a change in entropy of the working substance of Q hot over the temperature, T hot. And then from this one here, because we're rejecting heat out of the working substance, there'll be a negative heat transfer. So this will be Q cold over T cold. And that's still got to be equal to 0. So what we get, and this is only true for the Carnot cycle, is that Q hot over T hot equals Q cold over T cold. However, if we go back to our usual definition of efficiency, we said that it's what you get over what you had to pay. So that'll be equal to the work we get out of this over Q hot, which is our energy. Now, for any engine, the work you get out of it will be equal to Q hot minus Q cold by the first law. So this will be divided by Q hot. So for any engine, we can say the efficiency is 1 minus Q cold over Q hot. However, for a Carnot process, we saw that Q hot over T hot equals Q cold over T cold. So we can do a little cross multiplying action and get that Q cold over Q hot is equal to T cold over T hot. So our most efficient possible engine, our Carnot efficiency, is 1 minus, putting in the Q cold over Q hot in here, T cold over T hot, and make darn sure you work in kelvins or Rankine's, some absolute temperature scale here. But this is our maximum possible efficiency. It's the most that we can possibly get out of a perfectly reversible cycle. And perfectly reversible cycles are not achievable in practice. So this is a limit. So nothing will ever be this efficient, but it's an asymptotic limit. By the same token, we can also work out what the coefficient performance of a Carnot refrigerator would be. So remember, that is equal to Q cold over the work we got out of the system. By the first law, that's Q cold over Q hot minus Q cold. So this will be Q cold over Q cold minus, again, cross multiplying this around, we can say T hot over T cold, Q cold. Cancel the Q colds, do a little bit more algebra, and you get that the maximum efficiency of a refrigerator, Carnot refrigerator, or heat pump, is T cold over T hot minus T cold. Now, as we are heading into a world that is going to rely more on renewables, here's a thought about heating your house. Believe it or not, an air conditioner system is obviously a refrigerator. What that's doing is it's taking heat out from your house, which is cooler than the surroundings, and heating and transferring it out to the environment. But if you flip it around, you can say that you can imagine running an air conditioner the other way, where you're attempting to cool down the outdoors and reject the heat indoors. When you do that intentionally, that device is called a heat pump, and you can use that to heat the house. So here's the deal, is that the coefficient performance that you can get here can be bigger than 100%. So the energy that you provide is just moving heat from the hot reservoir, the outdoors, to the cold reservoir, the indoors. From the cold reservoir to the hot reservoir. Cold reservoir, the outdoors, to the hot reservoir, the indoors. you can move more heat than the work it took to move it. This is better than running a furnace. Running a furnace, the best you can do is hope to get all the chemical energy that you liberated burning the natural gas or whatever. You hope to get all of it out, 100% efficiency. So a coefficient performance of 1. You're never going to get that in practice. You're always going to have at least a little bit of loss, and at this point it's been engineered to about 98%, so that's as good as you can hope for. But with a heat pump, which is an air conditioning system that's designed to run backwards to move heat from outdoors to indoors, you can have coefficients of performance that are greater than 100%. You can move more heat than the work it took to move it. Now, the limit on this is how cold it is outside and what the difference in temperature is that you're trying to maintain. Now, at first, this may look awful, but keep in mind, these are absolute temperatures. So say it's freezing outside. If it's freezing outside, it would be 273 Kelvin outside. And let's say you're trying to keep it at at 20 degrees C, then we'd be looking at 293 Kelvin minus 273 Kelvin. So you're taking 273 and dividing that by 20. So in principle, you can move about 18 times, at max, you can move 18 times more heat than the work that you input to actually move it. In practice, you're not going to get anywhere near as good as that, but we're already at a point where the efficiency of this process pretty much matches the extra cost of the electricity to run a heat pump versus the natural gas to run a furnace. Going forward, as we transition more and more to renewables, the cost of electricity should go down relative. This is just a projection, but I'm guessing that it should go down relative to the cost of fossil fuels to keep the house warm. So something to keep in the back of your mind is that you may want, at some point when the furnace fails, you may want to at least investigate the possibility of installing some sort of a heat pump. Alrighty. So that will take care of our treatment of thermodynamics. I'll catch you over in the next videos.